Okay, today we are on lesson 5.3 notes, and it is on connecting F prime to F and F double prime with a graph of F. So in the first two lessons of the chapter, you learned about how to read a graph a certain way. So today we're going to connect what we learned in chapter 4 of all these first and second derivatives that we learned how to take, and now we learn to use them. So the handout you have is a much larger version of this. I don't have the legal size paper at home. So this is a miniature version, but totally to scale of the same exact thing you have in your hand. So your long sheet of paper should look like this, and you have this inside. So first thing you want to do is take the right-hand side, your right-hand side, where it says AB, AP Calc right here. You're going to fold that. See this dividing line? You're going to imagine a line right here and fold it down. So don't fold on any of the lines. You want to fold right in between. Okay, so fold right in between. Maybe it's easier to fold backwards first so you can see kind of right in between those two, and then crease it back the right way. All right, so you want to fold this side in. Okay, so fold this side in so you can see, oh, it says AP Calc, right, lesson 5.3, like so. Okay, once you have that side, the right side folded, that's your right side, then take the left side and come up to that crease that you just made. So come up to that crease. And unfortunately, if you are using a three-ring binder to hold on to your notes, then here's my suggestion. You have this pamphlet, right? In a sense, you have this pamphlet in front of you that you can take notes on, but it won't fit into your three-ring binder, right? So take a random sheet of paper, a blank sheet of paper. When you are done taking notes, glue, see how this is blank? This is the only side that's blank. Glue this down on that, and you can hole punch this, but you can access your notes. You can access your notes like so when you are completely done. Understand? Okay. So again, if you're keeping notebook, you can glue this in. If you're doing a three-ring binder, I would suggest to get a random sheet of paper, glue this down. But this you can still hole punch and put in your binder, but you can have access to the notes as it was intended. Okay. All right. So let's take a look at the notes here, right? The information in the front of your pamphlet tells you a little bit more. So when are you able to find a maximum or minimum of a graph? That is when your F prime is equal to 0. When your F prime is equal to 0, think about it. F prime is really your velocity. That's when your velocity is equal to 0. Using the example of hiking, when I said in class, when you're climbing a hill, you're hiking up a hill. Once you get to the top of the hill, you take a break. That's your velocity equaling 0, right? When you're coming down from the hill, going all the way up down to the bottom, you're going to reach the lowest point, and you take another break because you're going to head back up again. So you have your lowest point and your highest point where you have your velocity equal to 0. So that is how you are able to find your local maximums and your local minimums. That's when your F prime is equal to 0. F prime can also equal other things. F prime can be undefined, and we learned that in back in chapter 2. When is F prime undefined? Well, when you have a cusp, when you have a corner, or when you have a vertical tangent, or you have vertical asymptote, when the graph is actually broken up. So all that information is really helpful because then it helps me figure out what my graph is analytically, meaning algebraically. We cannot depend on a graph or a graphing calculator, because graph A, if you don't graph it right, it's not precise, right? And B, there's a huge part on the AP test that doesn't allow you to use a graphing calculator. So how do we do these things analytically, meaning just using algebra to figure out the information that's being asked of us? Okay. Keep in mind that when your F prime, right, when your F prime is minimum, right, when your F prime is not, excuse me, when your F prime is negative, your graph is decreasing. So when F prime is less than 0, that means F prime is minimum. Sorry, that means F prime is negative. It is decreasing this way. When F prime is positive, it is increasing, right? So we know the increasing right here. We know the increasing right here. We know decreasing looking like this, but it still doesn't give us enough information. So that's why we need to connect. That's why this lesson says connecting F prime to F double prime. You need a combination of F prime and F double prime to have enough information about your graph. So what does F double prime tell me? So F double prime, when F double prime is positive, right here, positive, it means it's concaving up. So concaving up looks like this, right? The whole thing, it's a whole bowl. Concaving up looks like this. It is a whole bowl. It's a whole smile. I say it's a whole parabola, right? Concaving down is when f double prime is negative. Negative is concaving down this way. So concaving up and concaving down. So f prime equals 0 means it's increasing. This is f prime greater than 0 is increasing. F prime less than 0 is decreasing. F double prime greater than 0 is concaving up. F double prime less than 0 is concaving down. So it's very important to know that you now need to combine information, right? Because in concaving up, my first example here, in concaving up, you actually have two things happening. You have decreasing and then increasing, right? In concaving down, you have both things too. You have increasing and decreasing. So we need both pieces. We need to know about the f double prime and f prime to figure out, ooh, what kind of curvature do I have here? And we'll really talk about this in number 6 in our notes today, okay? Now, you remember how to find maximum minimums using the first derivative, right? So there's a really good way to test whether it's maximum minimum without using intervals by taking your first derivative, extrema, and plug it into the second derivative. So if you plug it in, right? If you plug it in, you get a positive for your second derivative. Think about it. If your second derivative is positive, that means the concave up. That means then, this point right here, that's a minimum. If your second derivative is negative, that means it's concaving down. Hence, that point there is a maximum, right? So what your second derivative actually tells you what type of extrema you have without you having the more work of making a number line and testing points in between. So it's actually a shorter version of what you need to do. Okay, so this is number 1. We're going to see how to use this graph and connect it to what we've been talking about, which is f prime and f double prime. See what our information can give us. Now remember, this is an estimation because this graph, we cannot get exact values since we don't know the function itself. We don't know the equation of the function. It is with algebra and an equation of the function, then we can get actual exact value. So all we can do here is estimate, okay? So color pencils will be really good idea to figure out, to see the connections here, but again, totally optional, all right? So let's see what I am being asked here. I'm looking for when is f prime positive, when is f prime equal to 0, when is f prime negative, right? And then furthermore, part B, when is f double prime positive, when is f double prime equal to 0, when is f double prime negative. Okay, so I remind myself, again, first color I'm going to use is green. This is going to be the direction of my graph. So reading the graph from left to right, this graph was going down, and then up, and then down, and then up, right? I'm just following this graph here. So for me, I can see that it's negative this way until it hits this point right here. Then it went positive until it hit 0. Then negative again until this point right here. That's my lowest point. That's the valley, right? And then positive again. So when is it positive? It's increasing. So it's between this number to 0. That number looks like a little bit more than -1. So I'm just going to estimate. This is an estimation. So I'm going to say the interval from -1.1 to 0. And it looks like it picks up again from here up to infinity. So if 1.1, because this looks symmetrical, to infinity. So that's an interval. That's not a point. This is an interval from -1.1 to 0. This interval here is positive. From 1.1 to infinity, well, this way on, that is also positive. It is negative from negative infinity up to that point. So negative infinity up to -1.1. And then from 0 to 1.1, this is when my graph was going down. It's decreasing. So when was my graph 0? My f prime was 0 when I reached my minimum, maximum, and minimum. So when at x equals -1.1, x equals 0, 1.1. These are the points where my f prime is 0. Okay? All right. Now, how do I look for concavity? So second derivative tells me about concavity. Looking at this graph, I see that this graph has concaving up and concaving down. Here's where it gets a little bit tricky. I can't say this whole thing is concaving up to here because that point there is concaving down. So you see how you can't say the whole thing is concaving up and concaving down? Your concaving up and concaving down has to meet halfway between your graphs. So the safest bet is to look at your concavity and kind of pick a point in between and say, all right, it's concaving up halfway there, and then concaving down halfway, and then concaving up again. So concaving up means it's positive. Second derivative is positive. So it's from negative infinity to that point. That point looks a little bit more than half. So I'm just going to estimate 0.7. Again, this is an estimation, right? So from negative infinity to negative 0.7 looks like it's concaving up. And then from 0.7 again, positive 0.7 to infinity looks like it's concaving up again. Concaving down from negative 0.7 to 0.7. When is it equal to 0? Well, in our notes in our pamphlet up here, it says point of inflection. So the concavity changes. First of all, concavity has to change to get your point of inflection. So it has to change from positive to negative or negative to positive. But another piece is your f double prime has to equal 0 to get a point of inflection, what we call POI. It's just a lot quicker to say than point of inflection. So point of inflection happened in between my concavity here. So these 2 points I picked, so at x equals both positive and negative 0.7. Okay, so that's it for number 1. That's reading the graph of f. This is the original function. Okay, now let's see, use the graph of f prime to estimate intervals on which the function is increasing or decreasing, and estimate where f has a local extreme value. This is f prime. This is the graph of the first derivative. This is the graph of, if you want to think about it, velocity. So you have to think about it in terms of f prime, okay? So again, I'm going to help you see if we can interpret this a little bit better. So the function is increasing. F is increasing when f prime is positive. B says decreasing, that's when f prime is negative. When it has local extreme values, when f prime is equal to 0. Okay, now this graph is already f prime. So I can't look at it and say, oh, this is increasing, this is decreasing. No, this is already f prime. So what does it mean when f prime is positive? That means when the graph is above the x-axis, because that's when the graph itself is positive. When is this graph f prime positive? It's above the x-axis. Okay. When is f prime negative? Well, probably you can guess it. When the graph is below the x-axis. So it's neither above or below, it's on the x-axis. So graph on the x-axis. Okay, all right, so let's take a look at what I have here. When is my graph above the x-axis? My graph is above the x-axis from -2 to 0. And again from 0 to +2. We cannot include 0 because 0 itself is on the x-axis. So the interval where f prime is positive is -2 to 0 and 0 to 2. When is it below the x-axis? It is below the x-axis from negative infinity to -2 and from 2 to positive infinity, right? So negative infinity to -2 and 2 to positive infinity. When is f prime equal to 0? Okay, so f prime is equal to 0 at -2, at 0, and at 2. So at x equals -2, 0, and 2. Now be careful, not all of these are actual extremas. What am I talking about? At this point right here, my f prime went from a negative to a positive. So when I picture in my head, the graph went from decreasing to increasing. Okay, so that created a minimum. So a minimum at x equals -2. Here, the graph didn't change. It went from positive to positive, so no changes there. So that actually is most likely a point of inflection. So there's no extrema there. At +2, my graph went from positive to negative. So that means it went from increasing to decreasing. It went from this, so this is a maximum. So a maximum at x equals 2. We don't know the actual maximum and minimum y values because there is no equation of the graph here. This is just f prime. So this is how you interpret the graph if given to you as f prime. Okay, again, key point, this is f prime, not f, not the original function itself. Okay. All right, so let's do all this analytically. So let's see, use analytic methods to find the intervals in which a function is increasing, decreasing, concaving up, concaving down, find local extreme values, and find inflection points. So you can actually find, well, it's usually kind of A, B, and E goes together, and C, D, and F goes together, because A, B, and E you find from your first derivative, and then C, D, and E you find from your second derivative, okay? All right, if you want to color code, again, I totally suggest it, but it's entirely up to you. What I mean by color coding is I usually use the first derivative with one color, and the second derivative with a second color, so you can kind of see what is happening in each of the cases, okay? All right, so y prime is negative 6x squared plus 12x, right? So first thing we want to do, set equal to 0, because this is the first derivative test. So 0 equals negative 6x, you get x minus 2, set them equal to 0. So negative 6x equals 0, x minus 2 equals 0, x equals 0, x equals 2. All right, so then using this information here, I'm going to make a number line, put 0, put 2 in there. And the test is my first derivative test. I need to see which intervals are increasing and which intervals are decreasing. So f prime of something lower than 0, I put -1, because this is just test points, right? Something between 0 and 2, I'm probably going to pick 1. Something a little bit bigger than 2, I'm going to probably pick 3. All right, so these are f prime. Plugging into f prime, remember, we don't care about the actual values. We just care about whether the result is positive or negative. So it is easiest to plug it into the factor form, this one, all right? It's easiest to plug it into the factor form because all you have to figure out is what is my final product? What is the sign of my final product? If I plug in -1 to the first one, negative 6x, negative times negative gives me a positive, and a -1 minus 2 gives me a negative, so I get a negative. That means then this interval is decreasing because it's negative. Plug in a 1. Plug in 1 in the first one where it says negative 6x. So negative 6x times 1 is negative. 1 minus 2 is negative. So I get positive, so it's increasing. Plug in 3. Negative 6 times 3 is negative. 3 minus 2 is positive. This is going to be negative. So my graph looks something like this. It's decreasing, increasing, decreasing. Now, again, please do not get accustomed to, oh, the sign is always going to change back and forth. If it starts negative, it's going to go positive, negative. No. It doesn't happen that way. Sometimes the graph will go positive, positive, and negative. So don't have that state of mind of thinking, oh, these signs are always going to alternate. They don't always alternate like that. Okay. All right. Now let's see how to use my second derivative. All right. So let's see, y double prime. Y double prime is negative 12x plus 12. Okay, so that equal to 0. You get negative 12, and then I factor that, I get x minus 1. Well, negative 12, but divide both sides by negative 12, it doesn't do anything because there's no variable there. So you're really looking at x minus 1, so x equals 1. Okay, so again, I make my number line, put a 1 there, test a few points here because I need to see the concavity. So this is the second derivative test. So f double prime, I'm going to test 0 because it's to the left of it. F double prime is 0 if I plug it into this one right here, because that is your second derivative, not the next one. The next one you divide by negative 12. You can't lose that negative 12. You want to use the original equation. So if I plug in the 0, I get negative 12 times 0 minus 1, so that's negative. I get positive. So it's concaving up on this side. At double prime, I want to pick a number that is to the right of the 1, so 2, right? So if I plug in 2, and now using this equation right here, that's negative 12, and 2 minus 1 is positive, so that's negative, so it's going to concave down. Now, what is even better is that 0 and 2 are my extrema. They were my extremas from here. So that means then if plugging in 0 into f double prime gave me a positive, that means then it implies that 0 is a minimum because it is a concaving up, so it's a minimum. If plugging a 2 into my f double prime gave me a negative, that's concaving down, that gave me a maximum. So I now have all the information I need to graph this out and figure out all the answers, right? Now, even though it doesn't say to graph it out, I think your book does want you to graph. So the last thing you want to do is actually the final thing you want to do is really plug in some x values to get your some exact points. So what value should you plug in? You should plug in all the zeros that you got from your first and second derivative. So you should plug in 0, 2, you should plug in the 1, right? So these are actual points. So for points, I'm looking for f of 0, f of 1, f of 2. So this is why it's really nice to label these as f ofs, because you're plugging down to the original function here. So if I plug in f of 0, that's an easy one. That's a -3. If I plug in 1, I get -2 plus 6 minus 3. That gives me 1. If I plug in 2, this one requires a little bit more work. That's -2 times 8, so -16. Plus 6 times 4, that's 24, minus 3. Okay. Okay. So that would give me 24 minus 19, that gives me 5. Okay, so I have some exact points here that are very, very good. And we do want exact values. We do want these y values because we want them in my answer for the extreme values, right? Local extreme values. Okay. All right, so let's see. I would suggest to use graph paper. So we have the point 0, -3, 1, 1, 2, 5. Okay, so these are my 3 points. And it doesn't say much when you see these 3 points, because you think if you didn't have all this information that we figured out using our first and second derivative, you would think, oh, just draw a straight line through it. But it's really not a straight line, right? So we need to know that your graph is going decreasing. So my graph, based on my first derivative, I can kind of see this. My graph was decreasing and then increasing and then decreasing like this, right? Furthermore, it is a concaving up here. And then at 1, it changes, so it concaves down this way. Okay, so I kind of have an idea now. So I'm going to clean this up a little bit, because I know that this point right here is my point of inflection. So it's really helpful in terms of helping me draw my graph, because then I can say then, if that's a point of inflection, it concaves up on this side. It doesn't matter how wide out you go that way, really doesn't matter, just don't curve back in, okay? And then you concave down on the right-hand side like so. And that would be a sketch of the graph, okay? And last but not least, make sure you answer the question, because it wants all this information, right? So you want to find the intervals in which you are increasing, decreasing, concave up, concave down, local extrema. So in increasing, the interval of increasing, you look at your first derivative right here, your first derivative. Increasing is right here between 0 and 2. So you're going to say, for part A, my increasing interval is 0 to 2. Part B, where is it decreasing? Well, it decrease from -infinity all the way up to 0, and then from 2 on to infinity. So -infinity to 0, 2 to infinity. Where is it concaving up? And now we look at our second derivative. It was concaving up from -infinity up to 1. So -infinity up to 1. Where is it concaving down? From 1 to infinity. Where are my local extreme values? So here we're looking for my maximum minimums. So there was a minimum right here, which was a 0. So 0, -3 is the minimum. So be careful when you're writing this out. When you're writing this out, you would say you have a min value. Your minimum value is your y value. So min of -3 at x equals 0. And then here is your maximum. Maximum occurred at 2. So local max of 5 at x equals 2. So maximum of 5 at x equals 2. And last but not least, where is your point of inflection? We have one point of inflection at 1, and we have the value, y value of 1. So your inflection point is at 1, 1. That's your point of inflection, POI. Okay, and that concludes number 3. I know that was a lot of work for one problem, but notice how we didn't rely on any calculator. Now, of course, you can say, Ms. Chu, we could have just done a t-table and plug it in. You're right, but your curves may not be 100%, right? And there are some equations that are really hard to do a t-table for. So again, we start with an equation that is easier to tackle, that you could definitely check and see if you're on the right track. Then knowing that this is true for the easier polynomial functions, hence it is true for a lot more of the more complicated equations, right? So let's see, look at number 4. Number 4 looks like this, right? So again, be careful. Your first and second derivative is going to be a little bit different. What I would recommend here is, I actually would not recommend product rules, since you have one single term in the front. So I would actually go ahead and multiply this out. So I can just use power rule the whole way. So I would rewrite this equation as 5x to 3/4 minus x. Okay, now you're multiplying x to 3/4 times x. So that's 3/4 plus 1 more x. So 3/4 plus 1, that makes it 7/4. Okay, so now I'm going to use that to take my derivative. So y prime, the first derivative, is 5 times 3/4, so 15 over 4, x to the negative 1/4, minus 7 over 4, x to the 3/4. Right. So remember what I said about making it one fraction? This is where it's really useful because you really want to make it into one fraction. So this looks like 15 over x to the 1/4, minus 7 x to 3/4 over 4. Okay. Now, to get this to be common denominator, notice the right-hand side, all I need on the right hand is just another x to 1/4. And this will usually work out, meaning that your numerator now no longer has any rational powers, because x to 3/4 times x to 1/4 is really 3/4 plus 1/4, completing to be a 1. So 7x here. You have 4x to the 1/4. Okay. All right, now we gotta solve for the extrema. So you gotta set it equal to 0. How do you set a fraction equal to 0? You gotta solve for the top and bottom separately. The top will give you an extrema, most likely. The bottom, because that's when your first derivative is undefined, will give you the undefined points. Will give you the either the cusp or the corners or those weird situations, right? So you gotta set them separately. So 15 minus 7x equals 0. 7x equals 15. X equals 15 over 7, a little over 2. Okay, so at the bottom equals 0. 4x to 1/4 equals 0. Divided by 4 on both sides. You get x to 1/4 equals 0. Take the fourth power, x equals 0. So you have two numbers here, right? You still need to use it in your number line. All right, so 0 and 15 over 7. Okay, all right, now let's look at our first derivative test. So this is f prime test. We need to test some values to the left of 0. So I'm going to test -1. F prime of -1. Some value between 0 and a little over 2. So I'm going to pick 1. So f prime of 1. And since this is a little over 2, I can't pick 2. So I'm going to pick the next best number, 3. F prime of 3. Okay. All right. So I'm plugging -1. I'm plugging it into this one right here. Okay. So you plug it into the top, you notice that you get 15 plus a positive number, that's positive, but you can't take fourth root of a negative number. So there's no value here. I'm just putting an X there. There's no value here. You can put undefined if you want, but you know that then that means then nothing exists to the left of 0 of your graph, because you can't even do a test on it. So nothing exists on this side. Okay. Plug in 1, I get 15 minus 7, that's positive on top. And then I got 4 times the fourth root of 1 is going to be positive on the bottom. So my final answer is positive. So it's increasing right here in this interval. Okay. All right, plug in a 3. 15 minus 21 gives me a negative on top. 3 to the 1/4 power is still going to be positive answer. So it's going to be positive on the bottom. So it's going to be negative. I almost drew my arrow there. So it's going to be increasing and decreasing on this one. Okay. All right. Now venture on to my second derivative, right? So again, in this case, you want to go back to this pre-cleaned up form to take your second derivative, because it's a lot easier to take than this one. This one's in power rule form. This one's in quotient rule form. I don't think you want to do this. All right. So y double prime okay, so let's take y double prime. Y double prime is now 15/4 times -1/4. So -15 over 16, x and -5/4 minus 7/4 times 3/4. So 21 over 16, x to the -1/4. I know we're going to get a lot of fractions now. Get used to it. All right. So -15 over 16, x to the 5/4 minus 21 over 16, x to 1/4. Again, most of these you don't need to crisscross applesauce. Your denominators will have a lot of things in common. Notice you have x to 5/4 here and x to 1/4. So really all I need on the right-hand side is just another x. All right, I need one more x to make it so that it's the same power. So that would give me -15 minus 21x on top, 16x to the 5/4 on the bottom. Now set them separately equal to 0 like we did before. So negative 15 minus 21x equals 0. Negative 15 equals 21x. X equals negative 15 over 21, so negative 5 over 7. Set the bottom equal to 0. So you should know from the previous experience that that will get you 0, right? Okay. We can still make a number line with this. Negative 5 over 7, 0. Now you're probably thinking something, but we'll see. All right. So now this is F double prime test. We want to test a number to the left of negative 5 7. Well, negative 5 7 is not even 1 yet. So I'm going to plug in double prime of negative 1. And then this one's a little trickier. So what's in between negative 5 7 and 0? Negative 5 7 is a little more than half. So we can definitely pick a negative half in there. And then something to the right of 0, probably 1. We get F double prime. We're going to put it into this one, right? So again, the numerator gives us a pretty good answer. It's the denominator that's a little bit trickier. So when you're plugging in the values, the denominator is what's going to give us kind of a clearer picture here. The denominator is x to the 5th power 4th root. So it's whatever is negative to the 5th power is still going to be negative, but you cannot take the 4th root. So you can't take the 4th root of a negative number. So negative 1 is not going to work for us here. And negative 1/2 is not going to work as well. So not working, both of those not working. So there's nothing happening to the left of these, nothing, right? So X's or just nothing is fine. Just like here, there's nothing happening on this side, right? So 1, F double prime of 1, does that give me something? F double prime of 1 will give me a negative on top, and then 1 will give me a positive on the bottom. So it's concaving down the whole way, which kind of supports this, right? It's going increasing, decreasing. So that is a concaving down idea there. I think we have enough to answer our question, and we can also try to see if we can get some actual points here so that we can actually graph this out, right? Because graphing this out is kind of helpful. And we do need our exact value. We need some y values to talk about our extrema. So these are the actual points, right? So I'm going to use my space here, okay? So the only 2 points I really want to look at is this 15 over 7 and the 0, because these are the only true zeros. Oh, and 0, sorry. Yeah, 0's over here too. So 0 and 15 over 7 are the true zeros in my equation here. So F of 0, F of 15 over 7. F of 0 is nice because it's 0, because you plug in 0 here, because 0 times 5 minus 0 is still 0. 15 over 7 is a little trickier, right? So 15 over 7 is 15 over 7 to the 3/4 power times 5 minus 15 over 7. Well, we don't know what the exact value is, right? Because that is really a nasty answer there. Now, okay. But what you do know is 15 over 7 is a positive number to a odd power, and then 4th root that is going to be a positive number. 5 minus 15 over 7 is still going to be positive. So I'm going to say that this is a positive number greater than 0, obviously, right? So it's something above. Okay. Okay, so what do I have here? I have the value 0, 0, right? And I have the value 15 over 7, that's a little bit more than 2, so somewhere around here. And I know then the y value is somewhere positive. So notice on my y scale, I didn't even put down the number because I don't know what that number is. I don't want to rely on a calculator. So I know it's somewhere up here, okay? All right, so my graph, remember looking at my first and second derivative test, my graph is increasing, right? It's increasing up to that point and then decreasing from that point on because it nothing exists to beyond before 0, and this is concaving down because this is the behavior of the graph after 0. There's no point of inflection after that, so the whole thing is just concaving down. And it's increasing, decreasing, hence this is a maximum point for us, okay? All right, so time to now answer the questions. Okay, start with part A. Where is this graph? A is increasing, right? Yes, so we start with increasing. The interval of increasing is 0 to 15 over 7, right? That's my increasing interval right here. Okay, my decreasing interval is from 15 over 7 all the way to infinity, so 15 over 7 to infinity. All right, part C, when is my graph concaving up? None. It doesn't concave up at all, so no interval. All right. D, when is my graph concaving down? from 0 to infinity. The whole thing is concaving down. E, any local extreme values? Yes, I have a maximum, a max of this value right here. Kind of gross, but we can clean up just a bit. So 15/7 to 3/4. 5 minus 15/7. So 5 times 7 is 35. 35 minus 15 is 20. So 20/7 at x equals 15/7. That's my y value. Okay, and then last but not least, we're looking for the point. Oops, this is F, right? So point of inflection, there is none because the concavity doesn't change. So no POI. There's no point of inflection. Okay, all right, that's it for number 4. Okay, last one, number 5. So this one is a rational function. We're going to use our quotient rule to find our derivative. So y prime equals low d high minus high d low all over low squared, right? So you get x squared plus 1 minus 2x squared all over x squared plus 1 squared. That gives me 1 minus x squared over x squared plus 1 squared. Okay, you're going to solve these separately. So you're going to get 1 minus x squared equals 0. So that's 1 plus x. If you factor, 1 minus x equals 0. So x equals both positive and negative 1. The denominator, x squared plus 1 squared equals 0, won't give you anything because even when you take the square root, you get to this point, and you know that x squared will never be negative. You can even go one step further. You start taking the square root, you realize that doesn't get you anywhere. So actually, this one will not give you any weird points. There's no weird point of cusp or corner here. So we're only looking at positive negative 1. Okay, so we use positive negative 1 to make my number line. So negative 1, positive 1. Okay, so f prime test, first derivative test, testing something to the left of negative 1, so probably negative 2. F double prime negative, f prime, not f double prime. F prime of negative 2. What's a good number between those two numbers? 0. What's a good number after? Positive 2. Okay, plug it into this one. Now again, there's some quick shortcuts you can take. Notice the denominator here. No matter what number I put in, you're going to square it. So that's positive. Add a 1 to it, it's still positive. Then you're going to square that. So your denominator is always going to be positive. So I'll just draw a denominator and put a positive there. Okay. Now all I need to figure out is the numerator. So 1 minus negative 2 squared. So 1 minus 4, that is going to be a negative. So it's negative, that's decreasing. Plug in 0. So 1 minus 0, that's positive. So this is going to be positive, so increasing. And then plug in a 2, 1 minus 2 squared is negative. So I'm going to have a negative. So it's going like a curve, up, down again. Okay. All right, that's it for the first derivative. Let's go and look at the second derivative. So for second derivative, I would recommend to go to this one. It's the most cleaned up one, right? And you take the derivative with that one using quotient rule again. So second derivative, so you go low d high minus high d low. So be careful, the bottom has the chain rule. So take the 2 from the power. So x squared plus 1 to the 1 power now. Then the inside is, oopsies, the inside is x squared plus 1. So the derivative of that is 2x. So there's your chain rule there. All over the denominator squared. So x squared plus 1 squared squared. So that's the 4th power. Don't multiply the bottom out because it is not worth your time. Okay. All right, the top is a little messier. You do have to multiply things out. So I'm going to take it a step at a time. I'm actually going to FOIL this out first, then multiply it by negative 2x. All right. So negative 2x, I'm going to FOIL the next part out. That's x to the 4th plus 2x squared plus 1 minus, I'm actually going to go ahead and multiply these two out, right? Because these are opposite. This is 1 minus x squared. This is x squared plus 1. So that's going to give me 1 minus x to the 4th. And if I take these two times 4x, right? That will make it a little bit easier to work with. So the bottom still stays x squared to the 4th, right? All right, so I have negative 2x to the 5th minus 4x cubed minus 2x minus 4x. If you distribute the negative and the 4x, and then plus 4x to the 5th. all over. This is a lot of algebra. Yes, I know that, all right? So you get 2x to the 5th minus 4x cubed minus 6x all over x squared plus 1 to the 4th, all right? So you gotta solve, right? You gotta solve, set the top equal to 0. So the numerator, if you factor out 2x from both of them, from all of them, so you will get 2x times x to the 4th minus 2x squared minus 3 all over x squared plus 1 to the 4th. You set equal to 0. Okay, so this actually does solve really nicely. Believe it or not, you have 2x equals 0, so that gives you x equals 0. This next piece right here, this piece right here is actually quadratic, right? So that is x squared squared. So this is really hard to explain. So if you recall, you can actually set a different variable if this is easier to see. If you can say, all right, if x squared equals like a variable a, the thing that I highlighted there, that's actually a squared minus 2a minus 3. That factors into a minus 3, a plus 1. So if you put that back, it becomes x squared minus 3 equals 0, x squared plus 1 equals 0. And this one does, the first one does solve, x squared equals 3, x equals plus or minus root 3. This one doesn't equal 0, so that one doesn't give me the answer. So same thing with our denominator here, x squared plus 1 to the 4th also doesn't give me any answer. So for my second derivative, I have some good answers here, 0 and plus or minus root 3. So now my number line is looking like 0, negative root 3, and positive root 3. Okay, so let's see what are good f double prime test numbers. So you gotta know, negative root 3 is about 1.7. So what's a good number to the left of negative root 3? Probably negative 2. What's a good number between negative root 3 and 0? Negative 1. And then also positive 1, and then positive 2. Okay, all right. So again, I would most recommend doing it this way. This is the clean, most factored form, so it's a lot easier to test this. Also, same trick as before, your denominator here is always going to be positive because you squared it and then you fourth powered it. So for me, I can just put a positive on the bottom of my test here. Okay, the first term here, 2x, that x is your variable that actually determines your first sign. So negative, negative, positive, positive, depending on my number. So it's negative, negative, positive, positive. Okay, and now this one does require a little bit more work. If I plug in negative 2, I get negative 2 to the 4th, which is 16, positive 16, minus 2 times 2 times 2, so that would be minus 8, minus 3. So 16 minus 11 is still going to be positive, so I get positive here. So if we zoom in here, because it's such little space, but you have 1 negative, 2 positive, this is going to end up being negative, so it concaves down. Okay, plugging in negative 1 into this highlighted part again, so that's going to be a 1. 1 minus 2 minus 3, that's going to be a negative, so that's 2 negative and a positive, that's positive, so concave up. Okay, plug in positive 1, so 1 minus 2 minus 3 is also going to be negative, so that will give me 1 positive, 2 positives and a negative, so this is going to be negative, concave down. And then last but not least, plug in the 2, so 2 to the 4th, that's 16, minus 8, minus, so it's going to be positive here again, so that's positive, so concave up. So now we're going to actually need some actual points to figure out what this graph looks like. So we do have quite a few things on my number line here. Again, I don't know if you noticed this, but when I look at the actual points, I put them in order when I plug them in. So I'm going to plug in a negative root 3 first, and then the negative 1, and then the 0, and then the 1, and then the positive root 3. All right. So this is an easier way to go. So f of negative root 3, f of negative 1, f of 0, f of 1, f of positive root 3. Okay, so let's see. So I'm plugging into my equation here. I'm going to pick the easy ones to do. 0 over 0 plus 1, so that's still 0. That's great. Plugging in negative 1 over 1 squared plus 1, so negative 1 over 2, so negative 1 half. Plug in a positive 1, I get positive 1 over 1 plus 1, so positive 1 half. Okay, now plug in negative root 3, so let's see, negative root 3 over negative root 3 squared, so 3 plus 1, so negative root 3 over 4. Plug in positive root 3, you get positive root 3 over 3 plus 1, so positive root 3 over 4. All right, so again, you don't have to know exact values, but root 3 is about negative 1.7, right, or positive 1.7. So 1.7 over 4 is about 0.4, a little bit more than that, 0.4 something, okay? Okay, so looking at my values here, my graph doesn't need to be too big. I need from negative root 3 to negative 1. Okay, so it looks like I need negative 1, negative 2, negative 3 at most, so negative 3. So again, figuring out my scale. And then for my y-axis, I'm looking at my values here, and I got a half. Root 3 over 4 is about 0.4, so I don't need anything more than a half on both sides. So maybe I go like this. I think this is a pretty good scale for what I need, right? Okay, so let's go ahead and plug in my points here. I have negative root 3, so about 1.7, a little more than negative 1.5 here. And negative root 3 over 4, about 0.4, so probably somewhere around there. Okay, and then you have negative 1, you get, oh, sorry, I'm in the wrong spot. Negative 0.4 is down here, not up top. Apologies. And then you have negative 1 at negative half. You have 0, 0. You have 1 positive half. And then at root 3, a little bit further, you have about 0.4. So right around there. Okay. All right. So what does this look like? Wow, this is a lot of information, right? So this says concaving down and then concaving up, down, up. So it goes down, up, down, up. So this is the 0 there. So I know at least for the first 2 inflection points here, right? So for the first set here, from this point to this point is concaving up. That's the piece I just drew right there. Okay. And then concaving down is this piece right here. And why do I know that? Because if I take a look over here and see, I actually have a minimum here at negative 1 because it went from decreasing to increasing. I have a maximum here at positive 1, so it went from increasing to decreasing, right? So what about the other parts after that? Well, then beyond that point, it should be decreasing, but it's concaving down. So concaving down has, remember what I said, it has increasing and decreasing. So if it's just decreasing, that piece to the left of this point right here should look like that kind of curve. So it will curve like so. I know my arrow is that way because it's saying it's continuously that way, but it's going to be asymptotic to my graph. Remember, this is a rational function. Our knowledge from last year should still help us to know that there's an asymptote here at y equals 0. So it knows that it's going to curve this way because it's a concaving down, but this is a decreasing graph this way. And so vice versa, on the other side, it is concaving up, but still decreasing. So concaving up is decreasing, increasing. So the other side should look like this. So my other side of the graph should look something like this. It's going to be asymptotic to my y-axis. Okay, so again, I know this is a lot of work for this one problem, but this is a really, really accurate depiction of the graph, what the graph should look like. And if you don't believe me, you should go ahead and check. You can always check on Desmos and see if we're on the right track. Okay, all right, don't forget, we still need to answer our last part of the question, right? So start with part A. Where is this graph increasing? The interval is negative 1 to 1, right? So increasing from negative 1. And again, I want to show you from negative 1 to 1, that's where it's increasing, right? Okay, and then when is the graph decreasing? So the graph was decreasing from negative infinity up to negative 1, and then from 1 to infinity. So again, to prove, to kind of show you on the graph, it decreased here, right, and it decreased here. So negative 1 to negative infinity to negative 1, 1 to infinity, positive infinity, right? Part C, when is it concaving up? So looking at my second derivative test here, it concaved up from negative root 3 to 0, and from root 3 to infinity. And you wouldn't have known that unless you did this analytically. There's no way to see it from the graph, right? Part D, when is it concaving down? From negative infinity to negative root 3, and then from 0 to positive root 3. part E, where are my extrema? So we have some extrema. We had a minimum value. So min value of -1/2 at x equals -1. We had a maximum value of +1/2 at x equals +1. And last but not least, we have some inflection points because our concavity changed every single time. So we have point of inflection at a couple points. We have -√3, -√3/4 at 0, 0, and then at √3, +√3/4. So those are our point of inflections. Okay. All right, so that was how you would do it if you actually know the equation and you know how to take the first and second derivative using all those tests to help you find the graph of the function, okay? Now, last but not least, how about some pretend equation? You don't know a lot of information, but we can figure out this from this table of information that is provided for us, okay? All right, so find the absolute extrema of f and where they occur, find any points of inflection, sketch a possible graph of f. What can you conclude about f of 3 and f of -3? And this is brackets, okay? All right. So we're actually going to do this backwards. We're going to do part C first. Sketch a possible graph of f, okay? So the easiest ways to go about this is to look at the points and learn how to read the points. You have a point here at 0, 2, so 0, 2. You have a point at 1, 0, so 1, 0, and 2, -1, so 2, -1. So those are actual points, okay? Then you need to figure out the next piece. What does my graph look like? So in between 0 and 1, what does my graph look like? Well, f prime is negative, so it's decreasing. F double prime is positive, so it's concaving up. So using those two pieces, remember, concaving up is this and this. Which one is decreasing? So which one of these pieces is decreasing and also concaving up? It's this piece right here. That means then between 0 to +1, you're going to connect it looking like this, right? Curve like so, okay? All right, next piece, what does it say? Well, it says my first derivative is still decreasing, negative, but then this time I'm concaving down. So concaving down is this piece and this piece. Which one is decreasing? It's this piece right here. So that means then the next piece should be curved like so. Okay, and then lastly, it says that my derivative is positive, so it's increasing, still concaving down. So the concaving down but increasing looks like this, but be careful, it says my f value is negative. That means then my graph cannot go above the positive y-axis, so my graph is going to look something like this, but it's going to be like an asymptote. Okay, all right, now we do want to check a few things. First of all, let's take a quick look at my picture here. It says that f prime is 0 when x equals 0. So right here at this point right here, is f prime 0? Yes, because at an inflection point, my f prime can be 0, and f double prime must go to 0 at my inflection point. Beautiful. The concavity did change from positive to negative, so that's a good check. Secondly, at x equals 2, my first and second derivative are both d and e. Well, this point is a cusp. Should my first derivative be does not exist? Absolutely, because the cusp doesn't have a derivative, so that should be the case, right? Now let's go back to the first one. What about this d and e and this d and e? All right, give us a minute here because we didn't finish the graph. There's an important key piece that we missed here. It says f is an even function. What does an even function mean? It means that it is symmetrical about the y-axis. So what I have here is only the right-hand side of my graph. I gotta flip everything over and have a mirror image on the left-hand side. So it needs to curve this way, it needs to curve this way, and it needs to curve this way, right? So now I have the complete picture. Is this point right here also a cusp? Yes, therefore my f prime does not exist. My f double prime also does not exist. Okay, all right. Now with my graph complete, I can actually answer the questions. So let's see what it wants us to do in the directions here. So part A says, find absolute extrema. So what is the highest point of this graph? Well, the highest point is this one. That's an absolute maximum because none of the graph is going up above that line. So there's an absolute max of 2 at x equals 0. And then over here, these are my lowest points. I have 2 of them. So you can still say absolute because they're the exact same values here. So absolute min of -1 at x equals both positive and -2. Okay. All right. Part B. Have a point of inflection. Yes, a point of inflection is where your concavity changes. So here and here is your point of inflection because your concavity went from concavity up to concavity down. So the point of inflection at positive -1, 0. These are 2 separate points. I just wrote them as 1. Sketch a possible graph. We already did that. And part D, what can you conclude about f of 3 and f of -3? So f of 3, the value here should be the same as f of -3 because it's an even function. So f of 3 should equal f of -3. If this is an odd function, okay, so this is a teachable moment. If it's an odd function, then f of 3 will equal negative f of -3. So then it'll be the opposite. It will be the rotation about the y-axis, rotation about the origin. So it'll be like 180 degrees reflection of your function. Okay. All right, that was a long lesson. So hopefully you got through it all. If not, then make sure you rewind and check it out. Okay.